This lecture talks about the use of blocking in analysis of variance. Blocking is a technique that we use to control for known variability. An observable characteristic of subjects is used to define strata or blocks, and in each of them then we allocate the treatments in a completely randomized design. If we look at the model, we see that what we've done is, in addition to having an adjustment for treatments, we now have an adjustment for blocks as well. And we assume that the variations in all the observations come from a standard and consistent normal distribution. The advantage of blocking is that variation in the subject types is isolated from the variation due to treatments. So we've basically extended the sum of squares identity. And we see it here. The total sum of squares can now be broken into 3 parts: variation for the treatments, variation for the blocks, and of course whatever left over is the sum of squares for error. Let's look at an example. But first, when should we use blocking? Well, when subjects have an observable characteristic, it separates into a small number of categories, say sex, and the characteristic might influence the response. So for instance, sex and cardiac medication, we know that men and women respond to these things differently, so it would make perfect sense to go ahead and block in any sort of clinical trial or experiment involving this sort of thing. Now, it may also do this when experiment settings vary. That is, the experiment might use different locations, and location might have an effect, say in an agricultural experiment, okay? Or environmental conditions change during randomized runs. For instance, we may not be able to do all of our runs in a single day, and the temperature of the lab might change from day to day. Treatments are applied to different subjects. A really great study I read a few years ago compared the relative smoothness and efficacy of drill bits using different types of wood. Well, if you use a piece of wood as the block, you can use several different drill bits on that same piece of wood and do the comparison. Here's an example, and we'll start without blocking. We're going to look at something called a gauge study, which is basically an experiment used to calibrate precision measuring instruments. So we're going to measure 4 different tips in a hardness testing machine against 4 different metal coupons of the same composition. So basically the tip gets pressed into the coupon, and the depth of the hole made by the tip is a measure of hardness. And so we've got 4 different tips, 1, 2, 3, 4. We've done them in 4 different coupons. We've measured the depths, and we can see that there's some variation. But now we'd like to analyze this variation and see if there's a difference, tip by tip. So if we do an analysis of variance, we get a large p-value of 0.22, which indicates that there's no significant difference in the hardness measured by the tip. However, is there variation in the coupon hardness? Well, if we look at the hardness by coupon, we see that there's quite a bit of variation, so perhaps we should account for that in our analysis. So we'll block by coupon and rerun the ANOVA. And so we see the only difference here is that now we have an entry line for coupon, and we see that quite a bit of the sum of squares is taken up by coupon. And in fact, it's enough that it's statistically significant. But to the point, what we really want to know is about the tips. And we see now that the p-value for tips is very, very small. So there is a significant difference for tips. And that's the big payoff from using blocking. Now, we've used blocking in the past and not known about it when we used the paired t-test. So here's an example. We did a study to determine whether auto repair shop charges women more than they charge men. 20 shops were selected at random. 2 cars with the same make, model, and year and engine problem were assigned to a man and a woman respectively to get estimates. The estimates were compared with a paired t-test. So we paired them by shop. Now in the paired t-test, So we just compared the male and female estimates. We see that there's a significant difference. P-value is about 2.4 times 10 to the minus fourth. And here's our t-statistic, 4.5. Well, the t-test seems kind of complicated with all that subtraction and whatnot going on. How about if we just throw our measurements in and do an ANOVA with blocking, where we set the repair shops as the blocks? Well, we see that there's a very large amount of variation given over to the repair shops, rather smaller amount for sex. When we do the ANOVA, we see that the repair shop variation is not quite statistically significant, but the variation for sex is statistically significant. And look at this p-value, 2.4 times 10 to the minus fourth, the exact same p-value we got from the paired t-test. Now, is it a coincidence that the t-statistic, when it's squared, gives me the f-value? Well, not exactly, but I'll leave that for your course in probability and statistics.